Hi everybody, welcome back. In this video we're going to cover several important topics in Numpy, starting with understanding array dimensions and reshaping Numpy arrays. This is a very important topic, especially in deep learning, because the data we're going to process in neural networks often needs to be reshaped at various stages in the processing pipeline. We're going to cover this topic in more detail in future videos when we start working with Keras and TensorFlow directly, but it's important to establish a solid foundation of these concepts early on. So we're going to begin by defining the arrayInfo function that we introduced in the previous notebook, and notice that we've added an additional print statement to this function which prints out the dimension of the input array. We're going to start by working through several examples of reshaping data using the reshape function in Numpy, and notice first that the reshape function can be called using either syntax below. In this notebook, we'll be using the dot notation, which allows us to use an existing Numpy array to call the reshape method, in which we specify a tuple for the new shape of the array. The most important thing to remember here is that reshaping a Numpy array changes the shape of the array without altering the data itself. And as we'll see below, we can even change the number of dimensions in the array as long as the total number of data elements remains constant. In this first example, we're going to create a one-dimensional array using the aRange function that contains the integers 1 through 12 as shown below. Notice that the shape of the array is indicated by the tuple 12, and that the dimension of the array is just 1. All arrays in Numpy are defined by a tuple where each component of the tuple is referred to as an axis. So this one-dimensional array has just one axis. Also notice that A0 corresponds to the first element of the array. So next, let's use the reshape function to reshape this one-dimensional array into a two-dimensional array with 1 row and 12 columns as shown below. In this case, the tuple that defines the array is 1, 12, where the 1 corresponds to the first axis and the 12 corresponds to the second axis. So the array has two dimensions, and notice that when we print A0, we can now see that this corresponds to the data along the first axis, which in this case is the entire array from 1 to 12. When working with arrays, we often describe the first dimension as being the rows of an array, and the second dimension as being associated with the columns of an array. This is a helpful mnemonic for the first two dimensions, which correspond to the axis 0 and axis 1 respectively, but beyond that it becomes more abstract, and in higher dimensions we simply refer to them as axes. It's worth pointing out at this point that the word dimension is an overloaded term whose usage depends on the context. So for example, when we're referring to a two-dimensional array which can be represented as a matrix, we can refer to the array as having two dimensions or two axes. But the word dimension is also used specifically in mathematical contexts to describe the length along a particular dimension or axis. So in some cases we use the word dimension to describe the number of axes, and in other contexts we use the word dimension to describe the number of elements along a particular dimension or axis. In the next section, when we introduce tensors, we'll see that the word dimension is specifically used to describe the number of axes in the tensor, also referred to as the rank, whereas the number of elements along any particular axis is more commonly referred to as the length of an axis. So we just wanted to emphasize at this point that the use of the term dimension can sometimes be confusing, but once you understand that it's an overloaded term, it becomes much easier to sort out the terminology depending on the context. In the next example, we're demonstrating that we can also use the reshape function to achieve the same result, and instead of specifying explicitly the second dimension, which is the number of columns, you can just indicate a -1, which will create a single row with the appropriate number of columns. So sometimes this can be convenient when you're working with a large amount of data. We can also reshape the array to be 12 by 1, which would be 12 rows and 1 column. And notice now that the way we index into the array is different. So A0 now refers to the first row in the array, which in this case is just 1. So let's take a look at one more example below where we're going to reshape the array to be 3 by 4. Because this array has 12 elements, other possible transformations include 4 by 3, 2 by 6, and 6 by 2, since all of these are factors of 12. Next, we're going to take a look at working with multidimensional arrays with more than two dimensions, but the concept is still the same, and we'll see that reshaping higher dimensional arrays is no different than reshaping 2D arrays. Here we're defining a 3 by 5 by 2 array to emphasize that the first axis, which is 3, corresponds to the outermost bracket, and then the next axis, which is 5, corresponds to the next set of brackets, and then finally the last axis, which is 2, corresponds to the number of scalar values within the innermost brackets. In this second example below here, we're reshaping this 3-dimensional array into a 2-dimensional array of 3 by 10, and this is allowed since 3 and 10 are both factors of 30. You might say to yourself at this point, why would we want to reshape data in these various ways? And there's multiple answers to this. Arbitrarily reshaping data may or may not be meaningful for a particular data set, but oftentimes in deep learning, existing frameworks have a predefined shape for accepting various types of data. So take, for example, images, which have a height and a width and also one or more color channels. The order in which this data is stored is important, and it's also possible that in some stages in the processing that the image portion of the data may need to be represented as 2-dimensional arrays or collapsed into a single 1-dimensional array. We'll see some examples of this later in the notebook, and we'll also cover this in much more detail later in the course, but we just wanted to provide some motivation at this stage for why it may be necessary to reshape data. Let's now talk about adding a dimension to a Numpy array, which can be accomplished in a number of ways. Here we're creating a 1-dimensional array that contains the digits from 1 to 9, and then we're reshaping that into a 3 by 3 2D array. Next, we're going to use the reshape function to reshape the array to be 1 by 3 by 3, which is effectively adding a new dimension to the array along the first axis. Another way to add a dimension to a Numpy array is to use the expand dims function, in which we specify the array as the first argument and the axis along which we wish to create the new dimension as the second argument. In this case, we're going to specify axis equals 0, and so here we achieve the same result as we did above with the reshape function. Another approach we can use is to simply insert np.newAxis directly in the array at the desired axis location. So here you can see that we're adding a new dimension along the first axis. You might also notice that you could indicate none since newAxis is mapped to none, but it's preferred that you use newAxis because it's more explicit. For the same reason that we may need to expand the dimensions of an array, it's also sometimes required to remove redundant dimensions within a Numpy array, and we can do that with the squeeze function. So in this first example, we're creating a 1 by 3 by 3 array where the dimension along the first axis is redundant, and so that dimension can be removed by the squeeze function by passing in the array as the first argument and then indicating which axis should be removed from the array. Notice that it only makes sense to remove redundant dimensions which do not contain any data. In the next example, we're demonstrating that it's not possible to remove an axis whose size is greater than 1. So in this case here, if we attempt to remove the second axis, which has an index of 1, we'll get a value error as indicated below. So now let's come back to the reshape function and talk about a special case that we referenced above. Instead of specifying 2 explicit dimensions, you can specify a -1 for one dimension and then a specific value for the second dimension, as long as that value is a factor of the original size of the array. So in this case, we have a 1-dimensional array that contains values from 0 to 9, and we're going to reshape that array into 2 columns, which we can do by indicating a -1 for the number of rows instead of specifying 5 for the number of rows. And the reshape function will automatically generate 2 columns and 5 rows. Another example is provided below where we specifically indicate that we want 2 rows and we specify -1 for the number of columns rather than indicating 5 explicitly. So now let's talk about a reshaping example that's a little more concrete that has to do with flattening a portion of a Numpy array. Let's suppose that we have some 2-dimensional data that's associated with images. So in this case, we're going to create 3 4x4 2-dimensional Numpy arrays and store them in a 3x4x4 3-dimensional Numpy array. So in this example, we're notionally representing the 2D data associated with 3 separate images. And now let's scroll down to take a look at this figure of a well-known convolutional neural network called VGG16. Diagrams like this are often used to describe the architecture of a particular network. So in this case, at the far left, we're showing the input image, and then to the right of that, we're showing various layers within the network, and notice that each layer has a size indicated. As the data passes through the network from left to right, the shape of the data changes as shown in the figure. It's not important at this stage that we understand what these layers mean, but we just wanted to emphasize that as the data is processed through the network, the shape of the data is changing. For example, the data associated with the convolutional and max pooling layers in the first several stages of the network have a two-dimensional structure along with a depth, and the fully connected layers at the right-hand side of the network only have a depth. So for example, the data in the last max pooling layer, which has a shape of 7 by 7 by 512, is then flattened in the fully connected layer to the right, which has the same number of data elements, which is 4096. At this stage, we're simply providing this as a notional example of how reshaping data is a common operation when working with neural networks. So going back to our simple example, we can see below that we reshape the array to be 1 by 3 by 16, which is flattening the image portion of the data into a one-dimensional array while maintaining the other dimensions. Again, we'll cover this topic in much more detail later in the course, but we just wanted to provide an example for why reshaping data is often necessary. The next topic that we're going to cover is how to combine arrays, which can be accomplished with a few different methods in Numpy. The first method we're going to take a look at is the concatenate function. It takes two or more Numpy arrays as input, along with the axis for which the concatenation is to be performed. All the arrays must have the same dimension except for the dimension corresponding to the specified axis. In the first example below, we're going to create a 2 by 3 NumPy array and a 1 by 3 NumPy array, and then we're going to concatenate these two arrays along the first axis to create a 3 by 3 array. Notice that we could have specified more than just two arrays as long as all of the arrays have the same dimension other than the axis specified for concatenation. Next, we're going to take a look at two other types of functions that allow us to stack arrays either horizontally or vertically, which is a little more specific but also more convenient since you don't have to specify the axis. Stacking arrays horizontally is accomplished with the hstack function, which takes as input a tuple of arrays to be stacked. This amounts to concatenating arrays along the second axis unless the arrays are one-dimensional, in which case they are stacked along the first axis. In this first example, we're creating a 2 by 3 array and a 2 by 4 array, and we're using hstack to combine those two arrays into a 2 by 7 array as shown below. In the next example, we're creating two 3 by 1 arrays, and we're combining those horizontally to create a 3 by 2 array. So as you can see, stacking arrays in this way is very convenient and easy to use. Next, let's take a look at vstack to stack arrays vertically, and notice that the syntax is exactly the same as hstack. In the first example, we're going to create two 1D arrays and vertically stack them as shown below to create a 2 by 3 array. And then next, going back to one of our previous examples where we created a 3 by 4 by 4 array, we're going to show how we can reconstruct that in a different manner using vstack. So first we're going to create three 1 by 4 arrays, and then we're going to vertically stack those to create a 3 by 4 by 4 array. Although the concatenate function is a little more general, hstack and vstack are very convenient and easy to use because you only need to supply the input arrays. So that's all we wanted to cover in this video. In the next video coming up, we'll cover 3 additional topics in NumPy, which include element-wise operations, linear algebra, and array statistics. Thanks again, and we'll see you soon.